Hey guys, Dr. Brown here, and tonight we're working a differential equation relative to salt coming into a tank. It has certain flows in, flows out, and let's see how we would work that using a first order a linear differential equation and an integrating factor. Okay, now whoever came up with this, his pencil was sharper than mine for sure. Okay, this is a first order linear differential equation. dy dx plus, this is p of x, but just for clarity I've just listed it as p so it doesn't get cluttered. So dy dx plus p of x y equals f of x. Okay, the guy that came up with this said, hey, I need to transform the left side of this equation such that I can create a unique function that I can multiply this by that simplifies it. So he said, let my unique function be u. Hey, that's unique in itself. All right, so here he multiplied u by every term. So his thinking was, if I take the derivative of a function u times y, uy, if I take the derivative of that with respect to x, okay, I have the derivative, or first function, u, times dy dx, that's the derivative of the second one, plus the second one, which is y, times the derivative of the first one, du dx. And if I set that equal to the left side of this equation, you'll notice a few unique things. You have the term u dy dx. Of course, that was the derivative of these two, or derivative of the first one times the derivative of the second one. But you also have that here, u dy dx. So I could, in fact, subtract that out. Remove it, subtract it from the other, it eliminates it. So now I have du dxy. If all of this is going to be equal, du dx times y has to equal upy. So du dxy equals upy. Well, I have a y in both sides. If I divide that out, they're gone. So du dx equals up. For my derivative of my unique function, times y, the derivative of that, if to equal all of this, I'm now down to du dx equals up. I can separate the variables now, divide both sides by u, multiply both sides by dx, and then integrate those. So the integral of du over u, the integral of the derivative of a function over the function is the natural log of that function. So I'm left with natural log u equals the integral of p dx plus c1, my constant of integration. Now the author said you could solve for c1 or c in every case, but if you just let it, in this case, be 1, that works just fine for what we're trying to do. So that's what I did. So I raise this exponential to both sides. I'm left with u equals 1 times e to the integral p dx. And that becomes my unique function I can multiply by. So let's keep that in mind. And let's take this problem. And I'm having some sound trouble. Hopefully. All right, we have a tank, 500 gallon of water. And it's pure water. There's no mix of salt in it. So I have salt coming in at 2 pounds per gallon times the input rate of water, which is 5 gallons per minute. So if I multiply those two together, I get 10 pounds of salt per minute coming in. Okay? Big RI, rate in. And the rate going out, we're leaving the rate of water actually being pumped out is 10 gallons per minute. So if you just look at the rate coming in is 5 gallons per minute, the rate going out is 10 gallons per minute. So if I take the water rates in and out, subtract those, and multiply it times time, I end up with minus 5t gallons. Whatever my time is, if it's 1 minute, I'm 5 gallons less. If it's 2 minutes, I'm 10 gallons less. Okay, so my original tank volume is 500, which is what we were given, minus 5T gallons. So the rate at which salt's going out, AFT pounds per minute, times 10 gallons per minute. The gallons cancel here. That was 500 minus 10T gallons, I should have said. Gallons cancel, and I've got pounds of salt per minute, or what my units would be, pounds per minute. So I'm left with the rate of brine going out is 10T divided by 5. I factored the 5 out of the 500 here. 500 minus 5T, factor the 5 out. So I'm left then with 10T over 5 gives me, that's an A, sorry, not T. Can't read my own writing. All right, so I have 10, which is what I had coming in, all units are pounds per minute, minus 10A over 5 times the parentheses of 100 minus T. Okay, so that obviously 10A divided by 5 is 2A. So now I'll add the 2A over 100 minus T to both sides. So that becomes my first order linear differential equation. So the rate dA dt plus 2A over 100 minus T equals 10. And again, all units are pounds per minute. All right, so we had that integrating factor. And if you think about, well, what is this thing? Here's A, that's my variable. So the P of, in this case, P of T is 2 over 100 minus T. So my integrating factor is going to be E raised to the integral of 2 dt over 100 minus T. So if I let U be 100 minus T, du then is minus dt. So minus du equals dt. So then I can work through this, say, well, I have e to the minus 2, the integral of du. So there's my negative minus du. Okay, that equals dt over 100 minus t, which is u. So I have minus 2, e to the minus 2 natural log u, or e to the natural log u to the minus 2. And that becomes, the e cancels the natural log. I end up with u to the minus 2, which is 1 over u squared, which is 1 over 100 minus t squared. Okay, so let's get back over here. So I have the derivative of u, my unique function now, I have, which was 1 over u squared. So I have 1 over 100 minus t squared times a equals, you have to multiply that unique function by both sides here. So I end up with 10 over 100 minus t squared. Okay, so if I integrate both sides, the derivative over here drops. I have the integral here. Now I need to go through, okay, u is 100 minus t, du is minus dt, and I go through all of that again. And I end up with 1 over 100 minus t squared times a equals 10 u to the minus 1 plus c. Okay, let's go up here. All right, so we have 1 divided by 100 minus t squared equals 10 over 100 minus t plus c1. Now multiply then all the way through by 100 minus t squared. So it gives me 10 times 100 minus t plus c1, 100 minus t squared. But at when t was 0, remember the amount of salt in my tank was 0 because it was pure water. So 0 equals, and I multiply the 10 through, and obviously t is 0. T is 0 here. So I end up with minus 1,000 divided by 100 squared equals C1, which is minus 1/10. So now my salt as a function of time is 1,000 minus 10t minus, I think I've ran into my board here. It should be 100 minus t parentheses squared. All right, so you can see over time, let's say time becomes infinite. Well, it can't get infinite, because after when t equals 100 minutes, my tank is empty. That's as high as this thing can go. So it just 100 minutes as far as it can go. Okay, so 1,000 minus 10t minus 1/10 over 100 minus t parentheses squared is the function for the amount of salt at time t. And again, once we get up to 100 minutes, that's all we got. It's empty. All right, this is kind of fast. Sorry for that. But it's just use of an integrating factor, which is really a cool concept. To be able to come up with this to solve, to greatly simplify that problem. You end up with the derivative, you multiply the unique function, everything else goes away. Time, you multiply it, whatever u was times your variable, the derivative of all that equals then u times what's on the right hand side of that equation. And then if you just integrate both sides and then solve for C1, and then you have your equation. It's that simple. Okay, that's all for now. Why are we doing this? Together we're trying to build a better tomorrow, and do that how? Do that through math. This is why you take your calculus 1 and 2, your algebra, all that, trying to get to the point you can model real world situations. That's the key. Okay, that's all for now, and we'll talk to you next time. Thanks.